Today we're going to see an automaton that is the equivalent in power to the context-free grammar. The equivalence is analogous to the equivalence between regular expressions in automata, epsilon NFAs in particular. The automaton is called a pushdown automaton, or PDA, a term that was in use long before there were personal digital assistants. After describing the mechanics of the PDA, we'll talk about two different but equivalent ways that PDAs can define a language. We'll also mention the deterministic PDA, since the standard model of the PDA is the non-deterministic version, with epsilon transitions allowed. One of the key points to remember is that PDAs define all and only the context-free languages. But unlike finite automata, the non-deterministic version is strictly more powerful than the deterministic version, and only the non-deterministic version defines the class of context-free languages. However, the deterministic version is quite important in compiling, since parsers for programming languages usually behave like a deterministic PDA. Most programming languages are designed to be recognized by a deterministic PDA. For example, we mentioned previously the class of LL of 1 grammars, and such a grammar can be converted easily to a deterministic PDA. We'll get to a formal definition of a PDA shortly, but to start, think of the PDA as an epsilon NFA with an additional stack on which you can store symbols. Like any stack, you can only see the top symbol. The next move of the PDA is a function of three things. The move can depend on the state it is in, just like a finite automaton. The move also depends on the next input symbol, or the PDA may make a move on epsilon, that is, without regard to the next input symbol. This behavior is exactly like that of the epsilon NFA. But the thing that makes the PDA different from the finite automaton is that it has a stack of symbols chosen from a finite alphabet, and it can use the top symbol to help decide on the next move to make. Here is the image of a PDA we should keep in mind. At the center is the state. Like the state of the finite automaton, it controls what happens. There is some input which is waiting to be processed by the PDA. The PDA can only see the next input symbol and can use the symbol to help decide the next move. It also has the option to make the move on epsilon without consulting the input. And it has a stack of symbols. It can see only the top symbol and use that to help choose the next move. Moves of the PDA can involve a change of state, like the finite automaton, but it can also push or pop the stack. In any situation, that is, in some state with some next input symbol and some top of stack, the PDA has a finite number of choices of next move. Since it is non-deterministic, it is perfectly acceptable for there to be more than one choice. A move choice consists of a change in state, which could, of course, be to the same state it is in, a manipulation of the stack. At each move, the top stack symbol is replaced by a string of stack symbols. If the string is empty, it has the effect of popping the stack. If the string is of length 1, then the top stack symbol can be changed, or not, since the replacing symbol can be the same as the original. If the replacing string has length k greater than 1, we can see the move as a change of the top stack symbol, followed by k-1 pushes of symbols. Now we'll give the formal notation and usual symbols for the components of a PDA. There is a finite set of states for which we tend to use Q, just as for finite automata. There is a finite input alphabet for which we'll continue to use sigma. There's a finite stack alphabet, the symbols that can appear on the stack. For this alphabet we use gamma. There's a transition function delta to be described shortly. There is a start state, typically Q0 as for finite automata. There's a start symbol. This symbol is a member of the stack alphabet, and initially the stack contains only this symbol. And there is a set F of final states, again analogous to the finite automata. There are conventions for PDAs that are analogous to the conventions we made for automata and grammars previously. We continue to use lowercase letters at the beginning of the alphabet for input symbols. However, for PDAs, it is sometimes convenient to allow these letters to stand for epsilon as well as the symbols of the input alphabet. Capital letters at the end of the alphabet are stack symbols. Lowercase letters at the end of the alphabet are strings of input symbols. Greek letters at the beginning of the Greek alphabet are strings of stack symbols. We always write stack strings so the top of stack is at the left end. The transition function for a PDA has three arguments. The third argument is the symbol at the top of the stack. First comes a state, as for finite automata. Second, an input symbol or epsilon, as for the epsilon NFA's transition function. And last, a stack symbol. Delta for state Q, input A, which can be epsilon, and stack symbol Z, is a set of 0 or more actions. Each action consists of a next state P and a string alpha of stack symbols, possibly empty, with which to replace the top symbol Z. To summarize, when delta of Q, A, and Z contains P alpha, then one choice of move for the PDA when it is in state Q sees A at the front of the remaining input and has Z on top of stack is to go to state P, remove A from the front of the input. Of course, if A is epsilon, then the remaining input doesn't change, and replace Z by alpha on top of the stack. Note that although the PDA may have choices, several different P alpha pairs, it has to pick one pair and then do both things associated with that pair. It can't pick a next state from one pair and a stack string from another. Let's design a PDA for our favorite context-free language, the set of strings with the form 0 to the n, 1 to the n. Okay. We need three states. Q will be the start state. It represents the condition that we've so far seen only zeros on the input. P is the state we go to when we see the first 1. We use the state to remember not to accept a string if we ever see any more zeros. And F will be the final state. It's there only so we can accept when the number of 1s matches the number of zeros. We also need two stack symbols. Z0 is the start symbol. It has an important job. It marks the bottom of the stack. As we read zeros on the input, we will push one X onto the stack for each 0 we read. As 1s come in, we pop one X for each 1. So when the bottom marker, Z0, again becomes the top stack symbol, we know we have seen exactly as many 1s as there were zeros, so we accept. Here's the transition function of our PDA. Initially, Z0 is at the top of the stack. When we see the first 0, we push an X onto the stack. Notice that the replacement string is XZ0. That's that. That string replaces Z0, but the net effect is that the Z0 remains and X is pushed onto the top. Remember that stack strings are written with the top at the left. We remain in state Q as long as zeros appear on the input. After the first 0, each additional 0 causes the X on top of the stack to be replaced by two X's. Thus, the number of X's on the stack always equals the number of zeros read from the input. When a 1 appears at the front of the input, if X is on top of the stack, then we go to state P and pop the top X. Notice that there has to be an X on top of the stack, so if the first input is 1, when we still have Z0 on top of the stack, we have no move at all and can never accept. As long as more 1s appear on the input, we stay in state P and pop an X from the input. Thus, after seeing n zeros followed by m 1s, the number of X's remaining on the stack will be n minus m. And thus, after seeing n zeros followed by exactly n 1s, there are no more X's on the stack, and the top symbol becomes Z0 again. The last move of this PDA says that if we are in state P with Z0 on top of the stack, then without using any input, we go to state F. The Z0 remains on the stack, although that is not important. Here's a moving picture of the PDA we designed with 0001111 waiting on the input. Initially it is in state Q with just Z0 on the stack. That's the initial configuration. For the first move, we consume the first 0 from the input and replace Z0 by XZ0 on the stack. Notice the X is on top of the Z0. It's at the top of the stack. We consume another 0 and replace the top X by two X's. And the same thing happens again. Now the first 1 is consumed from the input. We transition to state P and pop the top X. Staying in state P, we consume another 1 and pop another X. Same thing. Now all the input is gone, but we have Z0 on top of the stack, so with epsilon input we can go to state F and accept. We're done, and we accepted the input string that was consumed, 000111. To talk more formally about the behavior of a PDA, we need the notion of an instantaneous description, or ID. The ID tells us the current state Q, the remaining input W, and the stack contents alpha. Again, remember that the top of the stack will be the leftmost symbol of alpha. There is an analogy between derivations for a grammar and sequences of IDs for a PDA. The IDs are analogous to the sentential forms of the grammar. In place of the double arrow, we use the turnstile symbol, that's this, to express the idea that one ID I can become another ID J by one move of the PDA. That is, suppose the first ID has state Q and input AW, where A is either the first symbol or epsilon, whatever is used for the next move, and it has stack X alpha, where X is the top symbol and alpha is then everything below that. Suppose the delta of QAX contains P beta. Okay. Then a possible next ID has state P, that's this. Okay. W is remaining on the input because A got consumed. Again, A may be a symbol or epsilon, doesn't matter. And with beta alpha on the stack, where the X here got replaced by the beta. We also have a goes to star relation for IDs defined analogously to the way we defined arrow star for sentential forms. That is, the basis representing 0 moves says that any ID goes to star itself. And for the induction, if I goes to J by some number of moves, possibly 0, and J goes to K by one move, then I goes to K by some number of moves. Here's the sequence of IDs that we get from our previous example. The input is 000111, so the initial ID has state Q, that input, and stack Z0. Here it is. The first move consumes a 0 from the input and pushes X onto the stack. So this 0 got consumed, that's what's left, and of course the Z0 is now on the stack. The second and third moves do the same. Okay, and you can see additional X's being pushed onto the stack. Okay. Next, because the next input is 1, the state becomes P and the 1 is removed from the input. Also an X is popped, okay, and that explains that ID. And 2 more moves pop the remaining X's, it's that and that. And then in the final ID, the state P has become F, and we accept. We can summarize the sequence by saying that the initial ID, this, goes to star the final ID, that. We can also say that any of these IDs goes to star itself and also to any of the IDs that follow in the sequence we just showed you. In order to understand better the idea of acceptance of an input by a PDA, we have to ask ourselves, what would happen if there were an extra 1 on the input? We'll take that up on the next slide. Okay. The sequence of IDs is the same, except that an extra 1 tags along at the end of each input string. The last move, where the state changes from P to F, is still legal, because a PDA can use epsilon input even if there is input remaining. State F has no transitions, so the sequence cannot be extended and the last 1 can never be consumed. We conclude that 0, 0, 0 followed by 4 ones is not accepted because the input was not completely consumed even though we entered a final state in the middle of the process of consuming the input. Okay. The normal way to define the language of a PDA is by final state. That is, L of P, the language of a PDA P, is the set of strings W such that when P is started in its start state, with W on the input and the start symbol on the stack, that's this ID, there is a sequence of moves of P that leads to an ID with a final state, there we are, with W completely consumed, that, and anything on the stack. I don't care. However, there is another way to define the language of a PDA, and this approach turns out to be rather useful, especially when we show how to convert PDAs to grammars and vice versa. We can talk about the set of strings that make the PDA empty its stack. This language is conventionally called NFP for a PDA P. The N stands for null stack, although we're not really going to use that term. Formally, this language is the set of strings W such that started in the usual ID with input W, that's of course this, P eventually reaches an ID in which it has consumed all of W and its stack is empty. Okay. We don't care about the state Q. It can be final or non-final, doesn't matter. Thus, every PDA defines 2 different languages in 2 different ways. However, the classes of languages defined by all the PDAs in these 2 ways are the same, and in fact are the context-free languages, as we shall see later. That is, if we have a PDA P that defines a language L by final state, then there's another different PDA P prime that defines the same language L, but does so by empty stack. P prime will presumably define a different language by final state, but that doesn't matter. The point is that every language defined by final state by some PDA is also defined by empty stack by some PDA. And conversely, if a language L is defined by some PDA P by empty stack, then L is also defined by some PDA P double prime by final state. Here's a rough idea of how we convert a PDA P accepting L by final state to P prime accepting L by empty stack. Basically, P prime will simulate P. That is, it does what P does with a few exceptions. If P prime finds that P is accepted by entering a final state, P prime empties its stack. Since P and P prime are in general non-deterministic, P prime can also guess that P will read more input. P prime will then not empty its stack in that sequence of moves, but rather will continue simulating P. But since P prime accepts whenever it empties its stack, and P might do that on inputs it doesn't want to accept, P prime needs a bottom of stack marker to prevent it from accidentally emptying its stack during the simulation of P. Thus, we'll give P prime all the states, symbols, and moves of P in order to do the simulation of P, plus a few other bells and whistles which we'll explain next. First, P prime has a new stack symbol x0. This is the start symbol of P prime, and it also has the job of guarding the stack bottom against accidental emptying. That is, if P empties its stack, P prime will find x0 on top of its stack and realize that P can make no move from this ID. Although being non-deterministic, it may have other ways to proceed. P prime thus does not empty its own stack. P has a new start state S and an erase state E. P prime has several additional transitions. This rule says that in its initial ID, it has only one choice. It must change to the start state of P and push Z0, P's start symbol, on top of its own start symbol X0, which remains to guard the stack. P prime is now ready and able to simulate P. Until P accepts, all the moves of P prime are the same as the moves of P, with the guard X0 sitting at the bottom of the stack unseen. And if P prime enters any final state F of P, then P prime has the option of entering the erase state E. It pops the current top of stack symbol, which might be X0 by the way. In that case, delta of F, epsilon, and X0 was previously undefined by P. Moreover, in the erase state E, P prime has only the choice to keep popping the stack and staying in state E. Eventually, P prime empties its stack and accepts. Now let's explain the construction in the opposite direction. That is, P accepts some language by empty stack, and we must design P double prime to accept the same language but by final state. P double prime also simulates P with a few bells and whistles. First, P double prime needs a bottom marker to detect that P has emptied its stack. If P double prime sees this marker at the top of the stack after its initial move, then it knows that P has emptied its stack, and so P double prime must accept by entering its own final state. P double prime has all the states, symbols, and transitions of P. In addition, P prime has a new start symbol X0 that also guards the stack bottom, just like it does for P prime. P double prime has a new start state S and a new final state F. From the initial ID, P double prime goes to the start state of P and pushes the start symbol of P onto its own stack. It is thus ready to simulate P. Once in the states of P, if P double prime ever sees the guard X0 at the top of the stack, it knows P is accepted. P double prime therefore goes to its own final state without reading any more input, and therefore accepts by final state the input that P accepted by empty stack. And a final word about the deterministic PDA. In order that there never be a choice of move, we certainly want the PDA to have at most one choice of move for any state Q, input symbol A, including epsilon, and stack symbol X. But we also have to rule out the possibility that there is a choice between using a real input symbol and making a move on epsilon. To be precise, for no Q in X can both delta of QAX and delta of Q epsilon X be non-empty. Such a PDA can have only one sequence of IDs, starting from the initial ID with a given input string. We generally assume acceptance is by final state, since if you accept by emptying your stack, you cannot ever process any more input if you're deterministic. While we shall not expand on the matter, the class of languages accepted by deterministic PDAs contains all the regular languages, obvious since it can simulate a deterministic finite automaton by just ignoring its stack, but it does not include all the context-free languages.